Hello friends, welcome to our channel. In previous video, we discussed about submetric space of a metric space. In today's video, we will discuss the sequences in the metric space and convergence of the sequences in a metric space. Sequences in a metric space. Let XD be a metric space with metric D a sequence AN in a metric space is a function from n to x, where n is the set of natural numbers, that is f n to x, such that f n is equal to a n for every n is belongs to natural number. Then a n is called a sequence in the metric space XD. For example, let R be the set of real numbers and D is usual metric on R, that is RD is a usual metric space. Then sequence AN is equal to 1 by n, such that n is belongs to natural number, is a sequence in usual metric space RD. Now the convergence of the sequence let XD be a metric space and AN is a sequence in XD. Then the sequence is said to be convergent to a point A belongs to X such that distance between A and A is less than epsilon for every n is greater than n naught, where n naught is any real number. That is, distance between A and A is tends to 0 as n tends to infinity. Or a sequence an in a metric space xd is said to be convergent to a point A belongs to capital X if for each epsilon greater than 0 there exists a positive integer n naught such that A naught belongs to sphere centered at A with radius epsilon for all n is greater than or equal to n naught, where S epsilon A is an open sphere centered at A in metric space XD. We can write it as AN converges to A as n tends to infinity, or limit n tends to infinity AN is equal to A. Note, if AN converges to A, then A is the only cluster point if sequence AN has more than one cluster point, then it does not convergent. That means a sequence is a convergent sequence if it has only one cluster point. If the sequence has more than one cluster point, then sequence is not a convergent sequence. Theorem a sequence in a metric space cannot converges two distinct limits. Or every convergent sequence in a metric space has a unique limit. Proof: let X D be any metric space and AN be the sequence in X. Suppose the sequence AN has two limits, that is limit n tends to infinity AN is equal to A and limit n tends to infinity A. We have to prove that A is equal to B. As AN converges to A, this implies for each epsilon greater than 0, there exists a positive integer capital N1 such that distance between A and A is less than epsilon by 2 for every n is greater than equal to N1. Put it equation number 1. As AN converges to B, this implies for each epsilon greater than 0, there exists a positive integer N2 such that distance between AN and B is less than epsilon by 2 for every n is greater than equal to N2. Put it equation number 2. Let capital N is equal to minimum of N1 and N2. Then distance between AN and A is less than epsilon by 2 for every n is greater than equal to capital N, and distance between AN and B is less than epsilon by 2 for every n is greater than equal to capital N. Now distance between A and B is less than equal to distance between A and AN plus distance between AN and B, because D is metric, which is equal to distance between AN and A plus distance between AN and B, because by symmetric property distance between AN and A is always equal to distance between A and AN, which is less than epsilon by 2 plus epsilon by 2 for every n is greater than equal to capital N. This implies distance between A and B is less than epsilon for every n is greater than equal to capital N, but epsilon is arbitrary and very small. Therefore, distance between A and B is equal to 0. Thus, A is equal to B. Hence, the sequence AN converges to a unique limit. Next theorem. A point A is a limit point of a subset capital A of the metric space XD if and only if there is a sequence AN of the points of A all distinct from A converges to A. In this theorem, XD be a metric space, a sequence AN converges to the point A if A is the limit point. Proof. Let XD be a metric space and AN be the sequence in XD. Let capital A be the subset of X and small a belongs to capital A is a limit point of the set A. We have to prove that the sequence AN converges to A, as A is limit point of capital A. So there exists R1 greater than 0 such that sphere centered at A with radius R1 intersect with A minus small a does not equal to phi, where SRA is sphere centered at A with radius R1. Consider R1 is equal to minimum of 1 and distance between A and A1. This implies R1 is greater than 0, less than equal to 1, and R1 is less than equal to distance between A and A1. This implies A1 does not belongs to sphere centered at A with radius R1. Then by definition, of limit point S R1A intersect with A minus A does not equal to phi, that is, there exists A2 belongs to capital A such that A does not equal to A2. Let R2 is equal to minimum of 1 by 2 and distance between A and A2. This implies R2 is greater than equal to 0, less than equal to 1 by 2, and R2 is less than equal to distance between A and A2. This implies A2 does not belongs to the sphere centered at A with radius R2. So, sphere centered at A with radius R2 intersect with A contains at least one point A3 does not equal to A. Continuing this process, we construct a sequence of real numbers A1, A2, A3 and so on, that is An of capital A other than small a, such that Rn is equal to minimum of 1 by n distance between An and A. Rn is greater than equal to 0, less than equal to 1 by n, and Rn is less than equal to distance between A and A. This implies An does not belongs to sphere centered at A with radius Rn. Then sphere centered at A with radius Rn intersect with A contains at least one point An plus 1 does not equal to A. Since distance between An and A is less than Rn minus 1 is less than equal to 1 by n minus 1. So, distance between An and A is tends to 0 as n tends to infinity. This implies the sequence An converges to the point A. Conversely, suppose the sequence An of the points of the set A converges to a point small a. We have to prove that A is a limit point of capital A. As An converges to small a, as the sequence An converges to the point A belongs to capital A. So, distance between An and A is less than epsilon for every n is greater than equal to n naught, where n naught is any positive integer. This implies An is belongs to sphere centered at A with radius epsilon for every n is greater than equal to n naught. So, sphere centered at A with radius epsilon contains infinitely many points of capital A other than A. This implies A is a limit point of capital A. it is sufficient for today's. In the next video, we will discuss some more results of the sequences, convergent sequences in the metric space. So keep in touch, watch our videos and subscribe our channel for more videos on these topics. Thanks to all. Have a nice day. Bye bye.